Picture a coin spinning in the air. While it spins, it is not heads. It is not tails. It exists in a blur of both possibilities at once, and only the instant it lands, only the instant you look, does it collapse into a single, definite outcome. For nearly a century, this strange behavior seemed like nothing more than a mathematical curiosity, a quirk buried in the equations of a handful of physicists trying to make sense of the subatomic world. Today, that spinning coin is the working principle behind machines that may soon solve problems no classical computer, no matter how powerful, could ever crack. Every device you have ever used to compute anything, from the calculator in a desk drawer to the most advanced supercomputer built by any government on Earth, speaks a single language. That language has exactly 2 letters, 1 and 0. Every photograph, every song, every line of this narration, every simulation of a hurricane or a protein or a nuclear reaction, is ultimately reducible to impossibly long strings of these 2 digits, flipped on and off by transistors etched into slivers of silicon. It is a language of certainty. A bit is either on or it is off. There is no in-between, no ambiguity, no blur. That certainty is precisely why classical computers are so reliable. And it is also precisely why they have a hard ceiling on what they can ever achieve by 2026. Engineers had spent decades shrinking transistors to sizes that were once considered physically impossible. Modern silicon transistors are now built at scales of just a few nanometers, so small that only a few dozen atoms separate one component from the next. At that scale, the tidy rules of classical physics begin to break down. Electrons no longer stay obediently inside the channels engineers designed for them. They tunnel through barriers that should be solid, leak current where none should flow, and introduce errors that get harder and harder to correct as the components shrink further. The relentless progress described by Moore's law, the decades-old observation that the number of transistors on a chip roughly doubles every couple of years, has been running into the hard wall of quantum mechanics itself. The very smallness that made classical computers powerful is now making them unpredictable. And that unpredictability is a signal. It is telling us that at the finest scales of matter, nature simply does not behave the way our machines assume it does. This is the point where a very different kind of unit enters the story, the qubit, short for quantum bit. A qubit does not have to choose between 1 and 0 the way a classical bit does. Instead, much like that spinning coin, it can exist in a combination of both states simultaneously, a condition physicists call superposition. This is not a metaphor for ignorance, as if the qubit secretly has a definite value and we simply do not know what it is yet. It is a deeper truth about the fabric of reality. Until it is measured, a qubit genuinely does not have a single, fixed value. It holds a spread of possibilities, weighted by probability, and it is only the act of measurement that forces it to settle into one outcome or another. The implications of this single fact are enormous. A classical bit can represent one of 2 states at any given moment, on or off, 1 or 0. A qubit, by contrast, can represent a proportional mixture of both 0 and 1 at the same time. String a handful of qubits together, and the number of states they can represent simultaneously does not grow in a simple, straight line. It grows exponentially. 2 classical bits can represent one of 4 possible combinations, but only one at a time. 2 qubits can represent all 4 of those combinations at once in superposition. Add a 3rd qubit, and that number doubles again to 8. By the time you reach just 50 qubits, the number of simultaneous states balloons past 1 quadrillion, a number so large it would take a classical supercomputer an impractical amount of time and memory to even represent, let alone process. This is why 2026 has become such a pivotal moment for the field. Classical computing is approaching physical limits that cannot be engineered away, no matter how clever the chip design becomes. Meanwhile, quantum computing is emerging from the research laboratory and into functioning, if still fragile, machines capable of tackling problems that were previously considered permanently out of reach. Pharmaceutical companies are using early quantum processors to model molecular interactions with a level of chemical accuracy that classical simulations struggle to achieve. Financial institutions are experimenting with quantum algorithms to optimize investment portfolios across scenarios that would take a classical machine centuries to fully explore. Materials scientists are simulating the behavior of exotic new compounds at the atomic level, searching for the next generation of batteries and solar cells. None of this would be possible without first understanding what a qubit actually is, and more importantly, what it is not. It is tempting to think of superposition as a kind of clever trick, a way of squeezing more computing power out of the same physical hardware. But that framing misses the far stranger and more important truth. The qubit is not a workaround. It is a window. It is one of the clearest, most direct pieces of evidence we have that the universe at its most fundamental level does not operate on certainty. It operates on probability. The coin does not become heads or tails because we cannot see it clearly enough. The coin, in some very real physical sense, is genuinely undetermined while it spins. Quantum mechanics tells us that this same undetermined nature applies not just to imaginary coins, but to electrons, photons, and the very particles that make up everything around us, including the atoms in your own body. If you find that unsettling, you are in good company. When physicists first encountered this behavior in the early 20th century, many of them, including some of the very scientists who helped discover it, were deeply uncomfortable with its implications. Understanding why requires stepping back nearly 100 years to a handful of strange experimental results that classical physics simply could not explain. Results that would eventually force an entirely new mathematical language into existence. One built not around certainty, but around probability itself. The story of the qubit really begins with light. In 1900, the German physicist Max Planck was trying to solve a problem that had frustrated physicists for years. A mismatch between theory and observation known as the ultraviolet catastrophe. Classical physics predicted that a heated object should radiate an infinite amount of energy at short wavelengths, an obvious absurdity that never matched what was actually measured in laboratories. Planck found that the mismatch disappeared if he assumed energy was not emitted smoothly and continuously, but in small, discrete packets. He called these packets quanta, and while he initially treated the idea as a mathematical convenience rather than a description of physical reality, the concept refused to go away. 5 years later, Albert Einstein took Planck's idea and pushed it further, using it to explain a puzzling phenomenon called the photoelectric effect, in which light striking a metal surface knocks electrons loose. Einstein proposed that light itself was made of these discrete packets, later named photons, each carrying a fixed amount of energy determined by its frequency. This was a radical claim. It suggested that light, long understood as a continuous wave, also behaved as a stream of individual particles. The evidence was undeniable, and it earned Einstein the Nobel Prize in Physics in 1921. not for his more famous work on relativity, but for this insight into the quantum nature of light. The strangeness deepened further with a deceptively simple experiment, involving two narrow slits cut into a barrier, when individual particles, whether photons or electrons, are fired one at a time toward those two slits. Common sense suggests each particle should pass through one slit or the other, landing on a detector screen behind in two clean, corresponding bands. That is not what happens. Instead, an interference pattern emerges, a series of alternating bright and dark bands, the exact signature you would expect if each particle were somehow behaving like a wave, passing through both slits simultaneously and interfering with itself. And if you place a detector at the slits to determine which path each particle actually takes, the interference pattern vanishes entirely, replaced by the two simple bands classical intuition originally expected. The mere act of observation changes the outcome. This single experiment, refined and repeated countless times over the past century, remains one of the most reproducible and unsettling demonstrations in all of physics. Trying to make sense of results like these, physicists in the 1920s developed an entirely new mathematical framework. In 1925 and 1926, Erwin Schrödinger introduced an equation that describes how the quantum state of a system evolves over time. And Max Born proposed the interpretation that would come to define the field, the value produced by Schrödinger's equation. Called the wave function, does not describe a definite physical property directly. Instead, it describes a probability. Specifically, the square of the wave function's amplitude at any given point gives the probability of finding the particle there if you were to measure it. This was the mathematical birth of the very idea now embodied in every qubit. Physical reality, at its most fundamental level, is described not by fixed values, but by probability amplitudes, spread across every possible outcome. Visualizing this can be genuinely difficult, because our everyday intuition is built entirely around classical, definite objects. Physicists solved this problem with an elegant geometric tool called the Bloch sphere, named after the physicist Felix Bloch. Imagine a globe, similar to the one you might use to look up countries and oceans. The north pole of this sphere represents the classical state 0, and the south pole represents the classical state 1, corresponding to the familiar off-and-on states of an ordinary bit. A classical bit can only ever sit at one of those two poles. A qubit, however, can be represented as a point anywhere on the entire surface of that sphere, and in a more complete sense, anywhere within its interior as well. Every point on the Bloch sphere corresponds to a unique combination of the two classical states, weighted by two numbers called probability amplitudes, one associated with 0 and one associated with 1. These amplitudes are not simple percentages. They are more like coordinates in a mathematical space that includes both magnitude and something called phase, a property with no true classical analog, similar to the offset between two waves. When a qubit's state is finally measured, the probability of it collapsing into a 0 or a 1 is determined by the square of these amplitudes, echoing exactly the interpretation Max Born proposed nearly a century ago. A qubit sitting exactly at the equator of the Bloch sphere, for instance, represents a 50% chance of measuring 0 and a 50% chance of measuring 1. The quantum equivalent of that perfectly balanced spinning coin. What makes this geometry so powerful is not simply that a qubit can occupy any point on that sphere while unobserved. It is that quantum operations, the equivalent of the logical gates that perform calculations inside a classical processor, correspond to precise rotations of that point around the sphere, where a classical logic gate flips a bit from 0 to 1 or leaves it unchanged. A quantum gate can rotate a qubit state to any orientation on the Bloch sphere, blending the two classical states together in a nearly infinite number of ways before a final measurement is ever taken. This is the deep reason a single qubit is fundamentally more expressive than a single classical bit. It is not just storing information, it is navigating a continuous mathematical landscape of possibility, and every calculation performed before measurement explores that entire landscape simultaneously. A property physicists call quantum parallelism, of course. All of this elegant mathematics would remain purely theoretical without a way to build something physical that actually behaves this way, translating an abstract point on the Bloch sphere into a real, controllable object, one made of actual atoms, electrons, or photons that can be manipulated, measured, and trusted to hold its quantum state long enough to be useful, has proven to be one of the most demanding engineering challenges of the 21st century. There is no single, agreed-upon way to build a physical qubit. Instead, several competing approaches have matured side by side, each with its own strengths, weaknesses, and passionate community of researchers. By 2026, two of these approaches had pulled ahead of the pack in terms of both scientific maturity and commercial investment: trapped ion qubits and superconducting qubits. Understanding how they differ reveals just how much raw engineering effort sits behind every quantum calculation. Trapped ion systems begin with individual atoms that have had an electron stripped away, leaving them with a net positive electric charge. These charged ions are then suspended in the near vacuum of a specialized chamber, held motionless in space by carefully tuned electric and magnetic fields generated by a device called a Paul trap, named after the physicist Wolfgang Paul, who shared the 1989 Nobel Prize in Physics for the technique. Once trapped and cooled to temperatures just a fraction of a degree above absolute zero using laser cooling, individual ions can be manipulated with extraordinary precision. Their qubit states are typically encoded in the energy levels of their outermost electrons, and researchers control those states using finely tuned laser pulses, nudging each ion's Bloch sphere point to precise new orientations. The great advantage of trapped ions is stability, because each qubit is a naturally identical atom, free of the manufacturing variation that plagues artificially fabricated devices. And because the ions are isolated in a near-perfect vacuum far from most sources of environmental interference, trapped ion qubits tend to hold their quantum states for remarkably long periods, sometimes tens of seconds or more, an eternity in the world of quantum information. This makes them exceptionally accurate, with very low error rates per operation. Companies such as IonQ and Quantinuum have built their commercial quantum computers around this approach specifically because of that reliability. The trade-off is speed. Manipulating ions with laser pulses and physically shuttling them between different zones of a trap for multi-qubit operations tends to be slower than the alternative. Superconducting qubits. Superconducting qubits take an entirely different physical approach. Rather than using naturally occurring atoms, engineers fabricate artificial atoms directly onto silicon or sapphire chips, using tiny loops of superconducting metal interrupted by a component called a Josephson junction, named after the physicist Brian Josephson, who predicted the underlying effect in 1962 at the age of just 22. When cooled to temperatures near absolute zero, these superconducting circuits lose all electrical resistance, and the Josephson junction allows electrical current to flow in ways governed by quantum mechanics rather than classical circuit theory. The resulting circuit behaves as an artificial two-level quantum system, one that can be manipulated not with lasers, but with carefully shaped pulses of microwave radiation, the same general category of electromagnetic wave used in a household microwave oven, though at drastically lower power and far more precisely controlled frequencies. The chief advantage of superconducting qubits is speed. Quantum gate operations on superconducting hardware can be performed in mere billionths of a second, orders of magnitude faster than the laser pulses used to manipulate trapped ions. This speed, combined with the fact that superconducting circuits are fabricated using techniques adapted from the conventional semiconductor industry, techniques that are, at least in principle, scalable to larger and larger chips, has made this approach the platform of choice for companies including Google, IBM, and Rigetti. The trade-off is fragility. Because superconducting qubits are artificial structures embedded in solid material rather than isolated individual atoms, they are more susceptible to microscopic defects, electromagnetic noise, and a general vulnerability to meaning their quantum states typically only survive for fractions of a millisecond before collapsing out of their delicate superposition due to unwanted interaction with the environment. This vulnerability to environmental interference is not a minor engineering inconvenience. It is arguably the single greatest obstacle standing between quantum computing as it exists today and quantum computing as it could someday become. The phenomenon is called decoherence, and it describes the process by which a qubit's fragile superposition breaks down as it interacts, even in the tiniest way, with the outside world. A single stray photon, a minuscule vibration in the supporting structure, even the faint thermal radiation given off by objects at room temperature, can be enough to disturb a qubit and destroy the delicate quantum information it was holding. This is why, regardless of whether a quantum processor uses trapped ions or superconducting circuits, both approaches require environments that are almost unimaginably isolated from the ordinary world. For superconducting processors especially, this isolation begins with temperature. The chips sit at the bottom of a device called a dilution refrigerator, a cylindrical structure built from a series of nested, progressively colder stages that resemble a metallic wedding cake more than a household appliance, using a specialized mixture of two isotopes of helium. These refrigerators are capable of cooling their innermost stage to temperatures around 10 to 15 thousandths of a degree above absolute zero, colder than the average temperature of empty interstellar space, and colder than anywhere else known to exist in the observable universe outside of a laboratory. At these temperatures, thermal vibrations that would otherwise disturb the qubits are suppressed almost entirely, giving the fragile quantum states a fighting chance to persist long enough to be useful. Trapped ion systems, meanwhile, achieve their isolation differently, relying on ultra-high vacuum chambers pumped down to pressures far lower than the near vacuum of low Earth orbit, combined with laser cooling techniques that use the momentum of carefully tuned photons to strip away nearly all of the ions. Residual thermal motion. In both cases, the underlying engineering challenge is identical. Build an environment so quiet, so still, and so free of outside interference that a genuinely quantum phenomenon, one that would otherwise be scrubbed away by the noisy chaos of ordinary conditions, has a chance to survive long enough to be measured and put to use. It is worth pausing here on just how counterintuitive this all is. We are not talking about miniaturized versions of ordinary computer chips. We are talking about apparatuses that recreate some of the coldest, most isolated conditions found anywhere in nature. Purpose-built to coax individual atoms or artificial circuits into briefly obeying rules that contradict our everyday experience of the world. If any of this has made you want to see how these ideas connect to the other frontiers of modern physics, from black holes to the nature of time itself, this is exactly the kind of channel built for that curiosity. And sticking around for what comes next will make the rest of this story click into place in a way that is genuinely satisfying. Once a qubit has been isolated, well enough to preserve its fragile state, it still needs to be controlled with extraordinary precision. For superconducting qubits, this control comes from microwave pulses generated by room temperature electronics and carried down through a carefully engineered chain of cables, filters, and attenuators into the coldest part of the dilution refrigerator. Each pulse shaped in both frequency and duration to rotate a specific qubit state to a specific new point on its Bloch sphere. For trapped ion qubits, the equivalent role is played by laser light, tuned to precise wavelengths that interact only with specific energy transitions inside the trapped ion, allowing researchers to flip, rotate, or entangle qubits with a level of control that would have seemed like science fiction only a few decades ago. These pulses are not simply switches, turning a qubit fully from 0 to 1 the way a classical logic gate might. They are finely calibrated instruments, capable of rotating a qubit's Bloch sphere point by any angle in any direction, creating the full spectrum of superposition states that give quantum computing its power. A pulse that rotates a qubit exactly halfway between its two poles, for instance, creates the perfectly balanced 50-50 superposition central to so many quantum algorithms. Slightly different pulses create different balances, different phases, different starting points for the calculations that follow. Every quantum algorithm ever devised, no matter how sophisticated, ultimately reduces to a carefully choreographed sequence of these pulses applied to one or more qubits, followed by a final measurement that collapses the accumulated superposition into a classical, readable answer, manipulating a single qubit, however impressive, only tells part of the story. The true power of quantum computing does not emerge from individual qubits acting alone. It emerges from a phenomenon so strange that Einstein himself refused to fully accept it, dismissively calling it spooky action at a distance. Entanglement. Entanglement occurs when two or more qubits become linked in such a way that the quantum state of one cannot be fully described without referencing the others, even if those qubits are later separated by enormous distances. Measure one entangled qubit and find it in the zero state, and you instantly know with absolute certainty what its entangled partner will show when measured, even if that partner is sitting on the opposite side of a laboratory, or, in principle, on the opposite side of the planet. This is not because some hidden signal travels between the two qubits at the moment of measurement. It is because, in a very real sense, the pair was never truly two separate, independent systems to begin with. They were, and remain, a single unified quantum object, described by one shared wave function, even while physically apart. The debate over what entanglement actually implies about the nature of reality occupied physicists for decades. In 1935, Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper arguing that this behavior implied quantum mechanics must be an incomplete description of reality, that there had to be some hidden underlying variables determining the outcomes in advance, variables simply unknown to the theory. This argument became known as the EPR paradox, and it set the stage for one of the great intellectual showdowns of 20th century physics, pitting Einstein's insistence on a definite, locally determined reality against the interpretation championed by Niels Bohr and the rest of the emerging Copenhagen school of quantum theory. The disagreement remained purely philosophical for nearly 30 years, until 1964, when the physicist John Stuart Bell devised a mathematical test, now known as Bell's theorem, that could actually distinguish between the two positions experimentally. Bell showed that if Einstein's hidden variables were real, measurements of entangled particles would have to obey a specific statistical limit. If quantum mechanics was correct, instead, that limit could be violated. Starting in the 1970s and continuing through increasingly rigorous experiments in the following decades, physicists including John Clauser, Aling Aspect, and Anton Zeilinger tested Bell's inequality using real entangled particles, and the results consistently, unambiguously violated the limit that hidden variables would have required. Quantum mechanics and its uncomfortably non-local implications. 1. This body of work was formally recognized with the Nobel Prize in Physics in 2022, awarded jointly to Clauser, Aspect, and Zeilinger for experiments that, in the words of the Nobel Committee, established the violation of Bell inequalities and pioneered quantum information science for quantum computing. Entanglement is not just a philosophical curiosity confirmed by Nobel-winning experiments. It is the essential resource that gives multi-qubit systems their extraordinary computational power. Recall that a single qubit exists in a superposition described by two probability amplitudes, one weighting the zero state and one weighting the one state. Two entangled qubits require four probability amplitudes to fully describe their combined state, one for each possible combination of 0 and 1 across both qubits. Three entangled qubits require 8 amplitudes. This pattern continues, doubling with every additional qubit, which means the amount of information needed to describe a fully entangled system of n qubits grows as 2 raised to the power of n. That this exponential growth is the mathematical heart of what researchers call quantum advantage, sometimes also referred to by the more provocative term quantum supremacy, the point at which a quantum computer can perform a specific calculation that would be effectively impossible for even the most powerful classical supercomputer to replicate in any reasonable amount of time. A system of merely 300 fully entangled qubits, purely as a thought experiment, would require more classical bits to describe its combined state than there are atoms in the entire observable universe. No classical computer, regardless of how large or how fast, could ever hope to simulate such a system directly, because there simply would not be enough matter in existence to build the memory required to store the description. Real demonstrations of quantum advantage have already occurred, though they remain narrowly focused on specific, carefully chosen problems rather than general-purpose computing tasks. In 2019, Google's Sycamore processor, a superconducting quantum chip containing 53 functioning qubits, performed a specific sampling calculation in approximately 200 seconds that Google's researchers estimated would have taken the world's most powerful classical supercomputer, at the time roughly 10,000 years, to complete. That specific claim was later challenged and revised downward by classical computing researchers who developed cleverer classical algorithms for that particular task. A healthy and ongoing back and forth that characterizes real scientific progress. By 2023 and 2024, subsequent generations of quantum hardware, including IBM's Eagle and Condor processors and Google's own updated Sycamore variants, pushed these demonstrations further, tackling problems increasingly resistant to classical simulation, even accounting for improved classical algorithms. It is worth being precise about what these demonstrations do and do not show. None of them prove that quantum computers are broadly superior to classical computers for everyday tasks like word processing, web browsing, or even most scientific calculations. Classical computers remain, and will likely remain for a very long time, the better tool for the vast majority of computational problems. What these demonstrations show is something narrower but still profound, that for certain carefully structured problems whose mathematical shape aligns naturally with quantum mechanical processes like superposition and entanglement, a quantum computer can achieve a decisive, sometimes almost unimaginable, speed advantage. The challenge, and the active frontier of current research, lies in identifying which real-world problems have that quantum-friendly mathematical shape, and then building quantum hardware reliable enough to actually solve them at a meaningful scale. Peter Shor's famous algorithm, developed in 1994, showed that a sufficiently large and stable quantum computer could factor large numbers, exponentially faster than any known classical algorithm. A result with enormous implications for cryptography, since much of the encryption securing modern digital communication relies on the practical difficulty of factoring large numbers. Loaf-Grover's algorithm, developed shortly after in 1996, demonstrated a different but still significant quantum speedup for searching unsorted databases. Neither algorithm can yet be run at the scale needed to break real-world encryption or search truly large databases, because doing so requires thousands of stable, low-error qubits working in concert, far beyond what even the most advanced quantum processors of 2026 can reliably sustain. But the mathematical proof that such speedups are possible in principle is precisely what has driven billions of dollars in research investment over the past 3 decades. Building toward that scale requires solving a problem separate from, but closely related to, decoherence, error correction. Every physical qubit, whether built from a trapped ion or a superconducting circuit, is imperfect. Its state can drift, its measurements can be misread, and its entanglement with other qubits can degrade before a calculation finishes. Classical computers also experience errors, but they can be corrected relatively easily by simply duplicating the information, since a bit that reads 0 can be checked against several backup copies also reading 0. Qubits cannot be copied this way. A foundational result called the no-cloning theorem, proven in 1982, shows that it is mathematically impossible to create an identical copy of an unknown quantum state without first measuring it, and measuring it would destroy the very superposition that made it useful in the first place. Quantum error correction gets around this restriction through a clever workaround. Rather than copying a single qubit, researchers spread the information it holds across many physical qubits, entangled together in redundant patterns that allow errors to be detected and corrected without ever directly measuring, and thereby destroying the underlying quantum information. The trade-off is steep. Current error correction schemes can require anywhere from dozens to well over 1,000 physical qubits to produce a single, reliable logical qubit, the kind of stable, low-error unit that large-scale quantum algorithms actually require. This is why headline announcements about processors containing hundreds, or even over 1,000 physical qubits, do not yet translate directly into a computer capable of running Shor's algorithm on a genuinely useful cryptographic key. The overwhelming majority of those physical qubits are, in effect, being spent on damage control rather than on the calculation itself. Real progress on this front has been steady rather than sudden, but it has been real. In December of 2024, Google's quantum team published results from a processor they named Willow, demonstrating for the first time that increasing the number of physical qubits dedicated to a single logical qubit actually reduced the overall error rate, rather than simply moving the errors around. This might sound like a modest technical footnote, but it represents a milestone the field had pursued for nearly 3 decades, crossing what researchers call the error correction threshold, the point at which adding more physical resources to a quantum system makes it more reliable rather than less. Below that threshold, scaling up a quantum computer only compounds its problems. Above it, scaling up genuinely improves performance, opening a realistic path toward the thousands and eventually millions of high-quality logical qubits that transformative applications like large-scale cryptography or full-scale molecular simulation would ultimately require. By 2026, competing hardware companies had each staked out their own roadmap toward this same horizon, sometimes with dramatically different philosophies about how to get there. IBM has pursued a strategy of steadily increasing physical qubit counts on superconducting chips while simultaneously refining more efficient error correction codes, aiming to reduce the overhead needed per logical qubit. IonQ and Quantinuum have leaned into the inherent stability of trapped ions, betting that fewer, higher quality physical qubits can outperform larger but noisier alternatives for specific near-term applications. Still, other companies have pursued entirely different physical platforms altogether, including photonic qubits, which encode information in individual particles of light and can, in principle, operate at room temperature, since photons do not interact strongly with their surroundings the way charged particles do, and neutral atom qubits, which use grids of laser light called optical tweezers to arrange and rearrange individual uncharged atoms with remarkable flexibility. Each of these approaches represents a genuine scientific wager about which physical system will ultimately prove easiest to scale, control, and protect from error, and it remains an open, actively contested question which platform, or combination of platforms, will dominate the field a decade from now. This diversity is not a sign of confusion or disorganization within the field. It reflects a healthy period of genuine scientific exploration, not unlike the earliest decades of classical computing, when vacuum tubes, mechanical relays, and early transistor designs all competed before silicon-based integrated circuits eventually won out. History suggests that periods like this one are exactly when the most important and least predictable breakthroughs tend to happen. Step back from the engineering details for a moment, and a deeper question comes into focus. Why does any of this matter beyond the walls of a physics laboratory or a technology company's research division? The answer lies in the specific mathematical shape of the problems a quantum computer is naturally suited to solve. And it turns out that shape appears throughout some of the most consequential challenges facing science and industry today. Consider the problem of simulating a molecule. Every molecule is, at its core, a quantum mechanical system, a collection of atomic nuclei surrounded by clouds of electrons, whose behavior is governed by the same probabilistic wave functions described earlier. Classical computers simulate molecules by approximating these quantum interactions using simplified mathematical shortcuts, because directly calculating the full quantum behavior of even a modestly sized molecule requires tracking an amount of information that grows exponentially with the number of electrons involved. The exact same exponential scaling that makes large entangled qubit systems so powerful. For small molecules, these classical approximations work reasonably well, but for larger, more chemically interesting molecules, the approximations become progressively less accurate, and the true quantum behavior, the behavior that actually determines how a molecule will react, bond, or catalyze other reactions, slips further out of reach. A sufficiently capable quantum computer sidesteps this problem in an elegant way, rather than approximating a quantum system using classical mathematics. It uses another quantum system, its own qubits, to directly emulate the quantum behavior of the molecule being studied. This is not a distant hypothetical. By the mid-2020s, research groups and companies had already used early, error-prone quantum processors to simulate simplified versions of catalytic reactions relevant to industrial ammonia production, a process that currently consumes roughly 1 to 2% of all the energy generated worldwide because the classical catalysts involved are so inefficient. Even modest improvements to that catalytic process, made possible by a clearer quantum mechanical understanding of how it actually works, could meaningfully reduce global energy consumption. Carbon capture chemistry presents a similarly promising target. The molecules capable of selectively binding to and removing carbon dioxide from the atmosphere or from industrial exhaust streams involve exactly the kind of complex electron interactions that classical simulation struggles to model precisely. Researchers working on next-generation carbon capture materials throughout 2025 and into 2026 have increasingly turned to hybrid approaches, using classical computers for the bulk of a simulation, while offloading the most quantum mechanically demanding portions, the parts where electron behavior is most complex and correlated to quantum processes. These hybrid quantum classical algorithms represent the practical reality of where the field stands today, not a complete replacement for classical computing, but a specialized accelerator for the specific pieces of a problem where quantum mechanics itself is the obstacle. Drug discovery follows a closely related logic, determining how a candidate drug molecule will actually bind to its target protein, a receptor or enzyme implicated in a particular disease, requires understanding the quantum mechanical forces governing that interaction at the level of individual electron clouds. Classical simulation tools have become remarkably sophisticated over the decades, but they remain fundamentally approximate. A quantum computer capable of directly simulating these interactions, even for relatively small molecular fragments, could help researchers identify promising drug candidates or rule out ineffective ones far earlier in the discovery pipeline than is currently possible, potentially saving years of laboratory testing on compounds that classical models simply cannot evaluate with full confidence. Beyond chemistry, optimization problems represent another category where the mathematical shape of quantum computing aligns naturally with real-world need. Many of the hardest problems in logistics, finance, and network design share a common mathematical structure, searching through an enormous number of possible configurations to find the one, or one of the few, that best satisfies a complicated set of constraints. Airlines scheduling crews and aircraft across a global network. Financial institutions balancing investment portfolios across thousands of assets under shifting market conditions. And telecommunications companies routing data through congested networks all face problems where the number of possible solutions grows explosively with the size of the system. Exactly the kind of exponential landscape where quantum algorithms, particularly a technique called quantum annealing, pioneered commercially by the company D-Wave, along with more general-purpose approaches called quantum approximate optimization algorithms, have shown early promise for finding good, though not always provably perfect, solutions faster than classical methods alone. Perhaps the most consequential application, and certainly the one that has drawn the most attention from governments and security agencies around the world, involves cryptography, and it cuts in two directions at once. On one hand, Shor's algorithm, once quantum hardware becomes reliable and large enough to run it on cryptographically meaningful key sizes, would be capable of breaking the mathematical foundation underlying most of the encryption currently protecting global digital communication, banking transactions, and government secrets, since that encryption relies precisely on the classical difficulty of factoring extremely large numbers. This looming possibility, sometimes referred to as Q-Day, the day a sufficiently powerful quantum computer first breaks real-world encryption, has driven an urgent, parallel research effort throughout the 2020s into what is called post-quantum cryptography. New encryption methods based on different mathematical problems believed to remain difficult even for quantum computers to solve. In August of 2024, the United States National Institute of Standards and Technology finalized its first set of standardized post-quantum encryption algorithms. And by 2026, financial institutions, technology companies, and government agencies worldwide were actively in the process of migrating their systems toward these new quantum-resistant standards. A race against a threat that, while not yet realized, is considered too consequential to wait for. On the other hand, the same quantum mechanics that threatens to break old encryption also offers a fundamentally new and, in principle, unbreakable form of it. Quantum key distribution uses the peculiar behavior of entangled particles to allow two parties to share a secret encryption key with a built-in guarantee. Any attempt by an eavesdropper to intercept and measure the particles carrying that key would unavoidably disturb their quantum state, in accordance with the same measurement principles described earlier in this documentary, revealing the intrusion immediately. This is not merely theoretically secure. The way classical encryption is secure only until a sufficiently powerful computer or a clever new algorithm comes along. It is secure as a direct consequence of the fundamental laws of physics themselves. China's Messias satellite, launched in 2016, demonstrated entanglement-based quantum key distribution across distances exceeding 1,000 kilometers. And by 2026, several countries, along with private companies, were actively developing and testing metropolitan-scale quantum communication networks, early building blocks of what researchers sometimes call the quantum internet, a future infrastructure layer that would allow not just secure communication, but the direct networking of quantum computers themselves, linking distant quantum processors into larger, more powerful, entangled systems than any single machine could achieve alone. Stepping back from these practical applications, however impressive, brings us to a deeper and more unsettled question, one that the qubit forces us to confront directly rather than politely set aside. What does it actually mean that the fundamental units of reality behave probabilistically rather than deterministically? This is not merely an engineering question. It is one of the oldest and least resolved questions in the philosophy of science, and physicists themselves remain genuinely divided over the answer. The interpretation most commonly taught in introductory physics courses, developed largely by Niels Bohr and Werner Heisenberg in Copenhagen during the 1920s, and now known simply as the Copenhagen interpretation, holds that a quantum system genuinely does not possess a definite value for a given property until that property is measured. Before measurement, only probabilities exist, encoded in the wave function. The act of measurement is treated as a fundamentally different kind of physical process, one that causes the wave function to collapse into a single, definite outcome. This interpretation is mathematically successful and experimentally consistent with everything observed so far. But it leaves open an uncomfortable question: what exactly counts as a measurement? And why should the act of observation hold such a privileged, reality-determining role in physical law? An alternative interpretation, first proposed by the physicist Hugh Everett in 1957 and now known as the many worlds interpretation, offers a strikingly different answer. Rather than treating measurement as a special process that collapses a wave function down to one outcome, Everett proposed that the wave function never actually collapses at all. Instead, every possible outcome of a quantum measurement genuinely occurs, each one unfolding in its own separate, non-communicating branch of reality. Under this view, a spinning coin does not resolve into heads or tails when observed. It resolves into both, but the version of you who observes heads and the version of you who observes tails now exist in causally separate branches of an ever-multiplying universal wave function, each entirely unaware of the other. This interpretation elegantly avoids the need for a special measurement process, since the entire universe, including the observer, is simply treated as one enormous quantum system evolving according to a single, never-collapsing wave function. But it comes with its own conceptual cost, an almost unimaginably vast, continuously branching multiverse, with no experimental way, at least so far proposed, to directly detect the other branches. A third major contender, known as pilot wave theory or the de Broglie bomb interpretation, developed initially by Louis de Broglie in the 1920s and substantially extended by David Bohm in the 1950s, takes yet another approach. It proposes that particles do, in fact, have definite positions and properties at all times, contrary to the standard Copenhagen picture, but that their motion is guided by an underlying wave function acting as a kind of pilot wave, steering the particle's trajectory in a way that reproduces all the same probabilistic, seemingly random outcomes observed in experiments. This interpretation restores a sense of underlying determinism, addressing exactly the discomfort Einstein originally raised in the EPR paper, but it does so at the cost of introducing what physicists call non-locality in an explicit, uncomfortable way. Since the pilot wave guiding a particle in one location can be instantaneously influenced by events happening to entangled particles arbitrarily far away. What is genuinely remarkable and worth sitting with for a moment is that all three of these interpretations, along with several others developed over the decades, make exactly the same experimental predictions. There is currently no known experiment capable of distinguishing between them, because they are not competing physical theories in the traditional sense. They are competing philosophical frameworks laid over the same underlying, thoroughly tested mathematics. This is precisely why physicists building and using quantum computers today, working with qubits and Bloch spheres and entanglement every single day, can largely set the interpretational debate aside entirely. The mathematics of quantum mechanics works with a level of experimental precision unmatched by any other theory in the history of science. Regardless of which philosophical story one tells about what that mathematics ultimately means, engineers can build a working qubit without ever resolving whether ever its branching multiverse is real, or whether Bohm's hidden pilot wave truly exists, or whether Bohr's collapsing wave function is the final word. The technology runs on the equations. The interpretation remains, for now, a question for philosophy of physics as much as for experimental physics itself. There is, however, one place where the strange behavior of qubits is not confined to the philosophy seminar or the physics laboratory, but appears to play out in the messy, warm, chaotic environment of living cells, and it has given rise to one of the more surprising interdisciplinary fields to emerge in recent decades: quantum biology. For years, the conventional assumption was that quantum effects like superposition and entanglement, so notoriously fragile and easily destroyed by environmental noise, could never survive in the warm, wet, chemically busy interior of a living organism, an environment about as far removed from a dilution, refrigerators near absolute zero isolation as one could imagine. That assumption has been increasingly challenged by a series of striking discoveries. Photosynthesis, the process by which plants and certain bacteria convert sunlight into chemical energy, appears to rely in part on a quantum mechanical effect. When a photon of sunlight strikes a photosynthetic pigment complex, the resulting packet of energy does not simply hop step by step through the surrounding molecular structure, the way classical intuition would suggest. Experimental evidence gathered since the late 2000s suggests the energy instead explores multiple possible paths through the molecular complex simultaneously, in a manner reminiscent of quantum superposition, before efficiently settling on whichever path delivers the energy to the reaction center with the least loss. Some researchers propose this quantum-assisted process helps explain the remarkably high efficiency of photosynthesis, an efficiency that has proven difficult to fully replicate in classical engineered solar energy systems, the mechanism birds use to navigate during long-distance migration presents another compelling, if still actively debated, example. Certain migratory species appear capable of sensing the Earth's magnetic field, using a light-sensitive protein in their eyes called cryptoglycan. The leading hypothesis, called the radical pair mechanism, proposes that absorbed light creates a pair of molecules with entangled electron spins, and the Earth's magnetic field subtly influences how that entangled pair evolves over time, ultimately affecting a chemical reaction whose outcome the bird's nervous system can somehow detect, effectively turning individual entangled electron pairs into a biological compass. This remains an active area of ongoing research, with strong but not yet fully conclusive experimental support, and it stands as one of the most tantalizing suggestions that the same quantum phenomena harnessed inside a dilution refrigerator might also be quietly at work inside a living organism. Whether or not quantum biology ultimately proves as significant as some of its proponents suggest, its very existence as a legitimate, actively funded field of research underscores an important point. The qubit is not some artificial, laboratory-only curiosity, isolated from the natural world by the extraordinary engineering required to build one. It is a direct expression of physical principles that appear to operate at least in some limited and specialized cases, even within biology itself, further reinforcing the idea that superposition and entanglement are not exotic exceptions to how reality works, but are, in some deep sense, closer to its default operating principle, simply obscured from everyday observation by the overwhelming noise and complexity of large, warm, classical systems beyond biology. The same delicate quantum properties that make qubits so difficult to build and maintain also make them extraordinarily useful as sensors, a field known as quantum metrology, because a qubit's quantum state is so exquisitely sensitive to its surrounding environment. The very fragility that engineers spend so much effort fighting against in a quantum computer becomes, in a sensing context, a tremendous asset. Quantum sensors built from trapped ions, superconducting circuits, or nitrogen vacancy centers in diamond, a defect in the diamond's crystal lattice that behaves as a controllable qubit at room temperature, have demonstrated the ability to measure magnetic fields, electric fields, gravitational variations, and time itself with a precision that exceeds the best classical instruments by orders of magnitude, atomic clocks, which are themselves a form of quantum sensor relying on the extraordinarily precise and stable energy transitions within individual atoms, have become so accurate by 2026 that the best experimental versions would neither gain nor lose a single second over a span longer than the current age of the universe. These clocks are not simply a curiosity for physicists chasing ever finer precision. Global positioning systems, the international financial infrastructure that time-stamps transactions across the planet, and fundamental tests of relativity itself all depend on timekeeping. Accuracy that traces directly back to the same quantum principles underlying the qubit. Quantum sensors are also being explored for early earthquake detection, for locating underground mineral deposits by measuring minute gravitational variations, and for medical imaging techniques capable of detecting the faint magnetic fields produced by neural activity in the brain with a spatial resolution far beyond what current technology allows. Despite all of this progress, it would be a mistake to think the fundamental challenges of quantum computing have been solved, with only routine engineering scaling left to accomplish. Several deep, unresolved problems continue to occupy the field's most capable researchers, and honest assessments from across the industry in 2026 generally agree that a large-scale, fully fault-tolerant quantum computer, one capable of running Shor's algorithm against real-world encryption or simulating genuinely complex molecules without error, likely remains at least 5 to 15 years away, with meaningful uncertainty on both ends of that estimate. One of the most persistent challenges is qubit connectivity. In principle, entanglement can link any qubit to any other qubit, regardless of physical distance, since entanglement itself does not depend on physical proximity in the way classical signals do. In practice, however, the physical hardware used to create and manipulate that entanglement, whether laser beams addressing trapped ions or microwave resonators connecting superconducting circuits, often works most reliably, and sometimes only works at all, between qubits that are physically close together on a chip or within a trap. This creates an engineering tension between the idealized mathematics of quantum algorithms, which often assume any qubit can be entangled with any other, and the physical reality of hardware where only neighboring qubits interact directly, requiring additional operations to shuttle quantum information across a chip, each additional operation introducing its own opportunity for error. A Second major challenge involves what researchers call crosstalk, unwanted interference between neighboring qubits that occurs simply because they are packed closely together to allow the interactions needed for entanglement and multi-qubit operations. A microwave pulse intended to manipulate one superconducting qubit can inadvertently nudge a nearby qubit as well, introducing subtle errors that compound as chip sizes and qubit counts increase. Solving this problem requires increasingly sophisticated chip designs, more precise control electronics, and error correction codes specifically engineered to detect and compensate for these correlated neighboring errors rather than treating each qubit's errors as entirely independent events. An assumption that simpler, earlier error correction schemes had originally relied upon. A third, more fundamental challenge concerns scalability itself. Every physical qubit added to a system, whether a trapped ion or a superconducting circuit, requires its own dedicated control lines, whether laser beams or microwave cables, each of which must ultimately route back to room temperature electronics outside the dilution refrigerator or vacuum chamber. As qubit counts climb into the thousands and eventually the millions required for large-scale fault-tolerant computing, the sheer physical challenge of wiring, cooling, and controlling that many individual quantum systems, while keeping every single one sufficiently isolated from environmental noise, becomes a formidable engineering problem in its own right, quite separate from the underlying physics. Researchers are actively developing cryogenic control electronics that can operate at the extremely low temperatures inside the dilution refrigerator itself, reducing the number of wires that need to cross the temperature gradient between the frozen quantum chip and the room temperature world outside. A promising but still maturing approach to this wiring bottleneck. There is also a genuinely open scientific question lurking beneath all of this engineering effort, one that connects back to the deepest foundations of physics itself: quantum mechanics and general relativity. Einstein's theory describing gravity as the curvature of spacetime remain famously incompatible at a fundamental mathematical level, each theory working extraordinarily well within its own domain. The very small for quantum mechanics and the very large and massive for general relativity, but breaking down or producing nonsensical results when applied together, particularly in extreme environments like the interior of a black hole or the earliest fractions of a second after the Big Bang. Some theoretical physicists have begun exploring whether concepts drawn directly from quantum information theory, the same mathematical framework describing qubits, superposition, and entanglement, might hold a key to eventually reconciling these two pillars of modern physics. This line of research, sometimes discussed under the banner of the holographic principle and explored through thought experiments involving black holes, suggests that the geometry of spacetime itself might, at the deepest level, emerge from patterns of quantum entanglement between more fundamental information-carrying units, not unlike qubits. Researchers, including Juan Maldacena, Leonard Su, and others have developed mathematical correspondences suggesting that a complex, gravitationally curved spacetime in one description can be mathematically equivalent to a flat space filled with entangled quantum information in another. This remains highly theoretical, an active area of fundamental research rather than an established result, and it should be treated with appropriate caution as elegant, promising mathematics rather than settled physical fact. But it hints at something remarkable: the same entanglement that a quantum engineer manipulates today between two nearby trapped ions or superconducting circuits may, according to some of the most ambitious theoretical work in modern physics, be conceptually related to the very fabric of space-time that holds galaxies together across billions of light-years, closer to the practical present. Researchers continue to debate the most efficient path toward useful, large-scale quantum computation. Some argue for continuing to push the raw number of physical qubits on a chip as high as possible, betting that sheer scale, combined with steadily improving error correction, will eventually cross the threshold into practical fault tolerance. Others argue for a more measured approach, prioritizing improvements in individual qubit quality and gate fidelity, the accuracy with which a single quantum operation is performed, over simply adding more qubits, on the theory that a smaller number of extremely high-quality qubits may prove more useful, sooner than a much larger number of noisier ones. Still others champion so-called modular architectures, linking multiple smaller, more manageable quantum processors together using quantum networking, techniques similar to those being developed for the quantum internet, rather than attempting to build one single, enormous monolithic chip. This diversity of strategy is not a symptom of a field in disarray. It reflects the genuine scientific uncertainty that surrounds any sufficiently new and difficult engineering challenge. Uncertainty that will only be resolved through the accumulated results of experiments still being run in laboratories around the world. Throughout the remainder of this decade, what is not in serious scientific dispute, however, is the underlying physics itself, the probabilistic, superposed, entangled behavior of the qubit has been confirmed through decades of increasingly rigorous experimentation, from the earliest Bell inequality tests in the 1970s, through the Nobel Prize recognized work of the 2022 laureates and beyond. The open questions concern engineering, scale, and application, not whether the fundamental quantum behavior itself is real. It is worth returning, briefly, to how the very idea of a quantum computer first came into being, because the origin of this idea reveals something important about how the qubit's strange behavior transformed from a physical mystery into a practical resource. In 1981, the physicist Richard Feynman, already famous for his contributions to quantum electrodynamics, gave a talk at a conference on the physics of computation in which he raised a deceptively simple observation. Simulating a quantum mechanical system on a classical computer, he pointed out, required resources that grew exponentially with the size of the system being simulated. Precisely the same exponential scaling problem described earlier in the context of molecular simulation. Feynman's proposed solution was elegant in its simplicity. If classical computers struggle to simulate quantum systems because they are not themselves quantum, why not build a computer that is quantum mechanical by its very construction? Such a machine, he reasoned, might be able to simulate other quantum systems naturally and efficiently, without ever needing to brute force its way through calculations that grow impossibly large on classical hardware. Feynman's proposal remained largely a theoretical curiosity for several years. A fascinating idea without a rigorous mathematical framework or any indication of what such a machine might be useful for beyond simulating other quantum systems. That changed in 1985, when the physicist David Deutsch, working at Oxford, formalized the concept mathematically, describing what he called a universal quantum computer, a machine capable, in principle, of simulating any physical process describable by quantum mechanics, and crucially, showing that such a machine could theoretically outperform any classical computer for at least some specific problems. Deutsch's work transformed quantum computing from an intriguing simulation shortcut into a genuine new model of computation, one that researchers could begin to formally analyze, compare against classical computing, and search for problems where its unique advantages might apply. The search for such problems bore its first genuinely explosive result in 1994, when Peter Shor, then working at Bell Labs, devised his now famous factoring algorithm. Before Shor's result, quantum computing remained an interesting theoretical exercise, largely confined to academic physics departments, valued more for what it revealed about the foundations of computation than for any near-term practical application. Shor's algorithm changed that overnight, because it demonstrated, with mathematical rigor, that a sufficiently powerful quantum computer could break the cryptographic systems protecting global digital security, transforming quantum computing from an academic curiosity into a matter of urgent strategic interest for governments, militaries, and intelligence agencies around the world. Research funding, both public and private, expanded dramatically in the years that followed, and the slow, decades-long process of translating Deutsch's abstract universal quantum computer into an actual physical device, built from trapped ions or superconducting circuits, and cooled to within a whisper of absolute zero, began in earnest. That decades-long translation from abstract mathematics to physical hardware is, in many ways, still ongoing today, and it is worth appreciating just how much has actually been accomplished along the way. The first experimental demonstration of a functioning to qubit quantum logic gate did not occur until 1995, performed by a team led by Christopher Monroe and David Wineland using trapped ions, work that would later contribute to Wineland sharing the 2012 Nobel Prize in Physics. At that point, building a quantum computer with even a handful of reliably controllable qubits was considered a major achievement worthy of significant press coverage. 3 decades later, processors containing hundreds, and in some architectures over 1,000 physical qubits have become an established, if still developing, area of commercial technology, with major corporations, well-funded startups, and national research programs across the United States, China, the European Union, and beyond all racing to push the field's capabilities forward. That international race carries implications that extend well beyond scientific prestige. Nations have come to view leadership in quantum computing much the way an earlier generation viewed leadership in nuclear physics or space exploration as a marker of broader technological and economic strength, with direct consequences for national security given the field's deep connections to cryptography and secure communication. China has invested heavily in both quantum computing hardware and quantum communication infrastructure, including the MISHA satellite program and a growing network of terrestrial quantum communication links connecting major cities. The United States has pursued a parallel strategy combining substantial federal research funding, channeled through agencies including the National Science Foundation and the Department of Energy, with a thriving private sector ecosystem of companies pursuing distinct hardware approaches. The European Union, alongside individual nations including Germany, the United Kingdom, and the Netherlands, home to a particularly strong tradition of experimental physics, dating back to the early 20th century pioneers of quantum theory, has similarly committed significant public investment to remaining competitive in what many policymakers view as a foundational technology for the remainder of the 21st century. This geopolitical dimension adds real urgency to a field that, at its heart, remains driven by an enduring scientific question: how completely can humanity learn to control and harness the probabilistic behavior that quantum mechanics revealed nearly a century ago. Every advance in qubit stability, every improvement in error correction, every new algorithm discovered represents another small step toward answering that question definitively, moving the qubit from a laboratory demonstration toward a tool as commonplace and reliable as the classical transistor became over the preceding decades. Yet for all of this remarkable technological progress, it is worth returning, in closing, to the more fundamental transformation the qubit represents, one that extends well beyond its considerable practical applications. For most of human history, and for the first several centuries of modern science following Isaac Newton's formulation of classical mechanics in the 17th century, the universe was understood as a fundamentally deterministic place, given complete knowledge of every particle's position and velocity at a single moment. Newtonian physics implied that the entire future of the universe, down to the smallest detail, could in principle be calculated in advance. This deterministic worldview, sometimes called Laplace's demon after the mathematician Pierre-Simon Laplace, who articulated the idea vividly in 1814, held that uncertainty was merely a reflection of human ignorance, a limitation of our knowledge and our instruments rather than a genuine feature of reality itself. The qubit stands as one of the clearest possible refutations of that deterministic worldview, not through philosophical argument, but through direct, repeatable, overwhelmingly confirmed experimental demonstration. A qubit's superposition is not a placeholder for our incomplete knowledge, waiting to be resolved by a more precise measurement or a more clever theory. Decades of Bell inequality experiments have shown, about as conclusively as any result in physics can be shown, that no hidden underlying variables exist that could restore Newton's tidy determinism. The coin genuinely is spinning, genuinely undetermined, right up until the moment it is observed. Probability, in the deepest sense available to modern physics, is not a description of our ignorance. It is a description of reality's actual behavior at its most fundamental scale. This has consequences that ripple outward well beyond the qubit itself, touching on how we understand causality, information, and even the nature of physical law. If the universe's most basic constituents behave probabilistically rather than then the seemingly solid, predictable world of everyday experience, tables and chairs and falling apples, must somehow emerge from that underlying quantum uncertainty, a process physicists call decoherence when discussed in the context of quantum computing hardware, but which operates continuously and universally all around us, all the time. As countless quantum systems interact with their environments and their individual uncertainties average out into the reliable, classical behavior we actually observe and depend on in daily life. In a very real sense, every qubit built inside a dilution refrigerator is not creating an artificial, exotic condition from nothing. It is carefully isolating and preserving a genuine feature of physical reality that exists everywhere, at every moment, but that ordinarily gets washed out by the overwhelming complexity and interconnectedness of the warm, noisy, classical world we inhabit. That perspective reframes the entire quantum computing enterprise in a way worth sitting with. Building a quantum computer is not simply an engineering achievement comparable to building a faster classical processor. It is closer to an act of translation, taking a fundamental property of nature, one that operates continuously in every atom, every photon, every electron throughout the universe, and learning to speak its native language directly, rather than working exclusively through the averaged, simplified, classical approximation that human technology has relied upon for its entire history up to this point. The bit, in this framing, was never truly the fundamental unit of information. It was always an approximation, a useful simplification that discarded the richer probabilistic reality lying underneath. The qubit is not an upgrade to the bit. It is closer to the truth. Much remains genuinely unknown. An honest science communication requires acknowledging the boundaries of current understanding rather than papering over them with confident-sounding claims that outpace the evidence. Physicists do not yet know which interpretation of quantum mechanics, if any single one, correctly describes what is actually happening during a measurement. And it remains entirely possible that this question will never be experimentally resolved, since all major interpretations currently make identical, testable predictions. Engineers do not yet know which physical platform, trapped ions, superconducting circuits, photonics, neutral atoms, or perhaps some combination or entirely different approach not yet fully developed, will ultimately prove most practical for large-scale, fault-tolerant quantum computation and reasonable. Well-informed experts across the field currently disagree on that question. Theoretical physicists do not yet know whether the tantalizing mathematical connections between quantum entanglement and the geometry of spacetime represent a genuine clue toward unifying quantum mechanics and general relativity, or merely an elegant but ultimately misleading mathematical coincidence. What researchers do know, with a level of confidence built on nearly a century of accumulated experimental evidence, is that the qubit's strange behavior is real, reproducible, and increasingly under human control. The distance traveled from Max Planck's reluctant 1900 proposal that energy comes in discrete packets, through Einstein's photoelectric effect, through the interference patterns of the double-slit experiment, through Schrödinger's wave equation and Born's probabilistic interpretation, through the EPR paradox and Bell's theorem and its Nobel Prize-winning experimental confirmation, through Feynman's proposal and Deutsch's formalization and Shor's algorithm, all the way to a functioning trapped ion or superconducting processor sitting inside a dilution refrigerator today, represents one of the longest, most carefully verified chains of scientific reasoning in the history of physics. Each link in that chain was tested, challenged, and confirmed by independent researchers working across different countries, different decades, and often different theoretical assumptions, and each link held. The years immediately ahead promised to test the next major links in that chain. Researchers across the field are working toward the milestone often called quantum advantage for practical, commercially relevant problems, moving beyond the narrow, carefully chosen demonstrations of the type Google's Sycamore processor achieved in 2019, and toward genuinely useful applications in chemistry, materials, science, an optimization that classical computers cannot match, not merely on an artificially constructed benchmark, but on a problem industry or science actually needs solved. Achieving that milestone will likely require continued steady progress on error correction, continued reduction in the overhead needed to produce reliable, logical qubits from noisy physical ones, and continued improvement in qubit connectivity and control precision. Incremental advances accumulating year over year rather than a single dramatic breakthrough arriving all at once. Alongside that engineering progress, fundamental physics research continues as well, probing deeper questions the qubit has opened rather than closed. Experiments testing the boundaries between quantum and classical behavior, searching for any sign that quantum superposition eventually breaks down on its own at some sufficiently large scale, independent of environmental decoherence, continue in laboratories around the world. Testing proposals, including one put forward by the physicist Roger Penrose, suggesting that gravity itself might play a role in causing wave function collapse for sufficiently massive objects, a hypothesis that remains unconfirmed but experimentally testable with increasingly sensitive equipment. Other researchers continue refining Bell inequality tests to close ever more subtle experimental loopholes, ensuring that the confirmed non-local behavior of entangled particles rests on the most rigorous possible foundation. Still others continue exploring the connections between quantum information theory and the deepest open questions in cosmology and gravitational physics, following threads first suggested by the holographic principle toward a more complete, unified understanding of physical law. There is something genuinely fitting about the fact that a concept born from questions about the nature of light and energy at the very smallest scales has grown, over the course of a single century, into a technology now being explored as a tool for understanding some of the largest and most fundamental questions in existence. From the molecular machinery of life itself to the geometric structure of space-time surrounding a black hole, the qubit did not simply give humanity a new kind of computer. It gave humanity direct, hands-on access to a layer of reality that had, for the entire span of recorded human history before the 20th century, remained completely hidden, operating quietly beneath the surface of the classical, deterministic world our senses and our intuition were built to perceive. We are, in a very real sense, still in the earliest chapters of learning what that access will ultimately allow us to do. The trapped ions oscillating in their electromagnetic cages, the superconducting loops carrying current without resistance at temperatures colder than deep space, the careful sequences of laser and microwave pulses rotating in visible points around an abstract mathematical sphere. All of it represents humanity's first tentative, painstaking steps toward fluency in a language the universe has been speaking since its very first moments. A language built not on the rigid certainty of 1 and 0, but on the richer, stranger, and ultimately more honest grammar of probability itself. What remains to be discovered, as that fluency deepens over the coming decades, is a question no current theory can fully answer, and that, perhaps more than any single practical application already achieved, is what makes this such a remarkable moment to be paying attention. It is worth taking a closer look at exactly how a sequence of qubit rotations translates into something a classical user can actually read and use, because the process reveals both the power and the peculiar limitation built into every quantum calculation. A quantum algorithm typically begins by placing a set of qubits into a carefully chosen superposition, often an equal blend of every possible classical outcome, effectively allowing the machine to explore an enormous space of potential answers simultaneously. The property called quantum parallelism described earlier. The algorithm then applies a specific, carefully designed sequence of quantum gates, precise rotations on the Bloch sphere, engineered so that the probability amplitudes associated with wrong answers gradually cancel each other out through a wave-like effect called destructive interference, while the amplitudes associated with the correct answer reinforce each other through constructive interference, growing steadily larger with each additional step of the algorithm. This interference-based amplification is the actual mechanism behind quantum computing's power, and it is worth stating plainly because it is often glossed over in popular explanations that focus only on the exponential number of states a qubit system can represent. Simply having access to an enormous superposition of possible answers does not, by itself, provide any advantage, because a direct measurement of that superposition would simply return one random answer out of the vast number of possibilities, with no better odds of correctness than blind guessing. The entire art of designing a quantum algorithm lies in engineering the interference pattern so precisely that, by the time a final measurement is taken, the probability of reading out the correct answer has been mathematically boosted far above what random chance would suggest, while the probability of reading out every wrong answer has been suppressed correspondingly. Grover's search algorithm accomplishes exactly this for the problem of searching an unsorted list, repeatedly applying a specific quantum operation that amplifies the amplitude of the correct entry while suppressing all others, achieving a quadratic speedup over the best possible classical search, a smaller but still meaningful advantage compared to the exponential speedup Shor's algorithm achieves for factoring. This interference requirement also explains, in a fairly direct way, why decoherence is so uniquely damaging to a quantum computation. Beyond simply corrupting individual qubit values the way noise corrupts a classical signal, interference depends on maintaining precise relationships, called coherence, between the different components of a superposition across the entire duration of a calculation. If even one qubit in the system loses its coherence partway through, if it becomes even slightly entangled with some stray, uncontrolled particle in its environment rather than remaining cleanly entangled only with the other qubits, intentionally involved in the calculation, the delicate interference pattern the algorithm was carefully engineering can collapse prematurely, and the final measurement reverts toward random noise rather than a confidently amplified correct answer. This is why quantum engineers describe coherence time, the duration a qubit can maintain its quantum state before as being just as important a metric as raw qubit count, and in many respects more important, since a large number of poorly coherent qubits is far less useful than a smaller number of qubits that remain coherent long enough to complete a meaningful calculation. A newer and rapidly growing area building on these same principles is quantum machine learning, an active research field exploring whether quantum interference and entanglement can be harnessed to accelerate the pattern recognition and optimization tasks that underlie modern artificial intelligence. Classical machine learning models identify patterns in data by adjusting an enormous number of internal parameters through repeated exposure to training examples, a process that, for the largest modern models, requires staggering amounts of classical computing power and energy. Some proposed quantum machine learning algorithms suggest that certain types of pattern recognition tasks, particularly those involving data that is naturally high-dimensional or that has an underlying mathematical structure resembling the interference patterns quantum computers naturally produce, might be accelerated using quantum hardware. This remains one of the more speculative applications discussed in the field, with a genuine and ongoing scientific debate about how much of a practical advantage quantum approaches will ultimately offer over increasingly sophisticated classical machine learning techniques. And honest researchers in the field are generally careful to present this as a promising area of active investigation rather than a settled or guaranteed advantage, regardless of exactly which application ultimately proves most transformative. The growth of quantum computing as a field has created a parallel need for an entirely new kind of workforce, one that did not meaningfully exist a generation ago. Universities around the world have rapidly expanded degree programs and specialized courses in quantum information science throughout the 2010s and 2020s, training physicists, electrical engineers, and computer scientists in the specific blend of skills needed to design, build, and program quantum hardware, a discipline that draws simultaneously on quantum mechanics, low-temperature physics, microwave and laser engineering, and an entirely new style of algorithm design fundamentally different from the classical programming techniques most computer science students have traditionally learned. This expanding talent pipeline represents its own kind of infrastructure investment, one that will shape how quickly the field's theoretical promise translates into practical, widely available technology over the coming decades. Since even a perfectly engineered quantum processor is only as useful as the community of researchers and engineers capable of programming it to solve genuinely valuable problems. There is a final thread worth pulling on before this story comes to rest, one that returns us to that spinning coin from the very beginning. The reason superposition feels so foreign to human intuition is not because it is rare in nature. It is because human beings, and every other large, warm, classical object we interact with directly, are themselves the product of countless trillions of quantum interactions, averaging out into predictable, stable behavior through the process of decoherence, moment by moment, continuously, everywhere. We do not experience the underlying quantum uncertainty of the world not because it is absent from our lives, but because we are, in a sense, built entirely out of its aggregate consequences, insulated from its raw strangeness by our own overwhelming physical complexity. A single trapped ion, cooled and isolated inside a vacuum chamber, is in this light not an artificial anomaly built by clever engineers defying nature. It is closer to a rare, carefully preserved glimpse of how a single particle behaves before the rest of the universe has had the chance to. Average that behavior away. That reframing carries a certain quiet significance for anyone who has ever wondered whether the universe operates by fixed, comprehensible rules, or by something closer to chance. The honest answer, delivered through nearly a century of increasingly rigorous experimentation and now embodied in working machines capable of practical computation, is that it operates by both simultaneously, in a way that classical intuition never anticipated and still struggles to fully absorb. The rules are real, precise, and mathematically exact, expressible through wave equations and probability amplitudes with extraordinary predictive accuracy. But what those exact rules govern is not a definite, predetermined outcome. They govern a landscape of genuine possibility, weighted and shaped with mathematical precision, collapsing into a single, observed reality only at the moment observation actually occurs. The qubit is, in the end, neither purely a triumph of engineering nor purely an abstract philosophical curiosity, but something that manages to be both at once. It is the point where the strangest, most carefully verified discovery of 20th century physics meets the practical demands of 21st century computation, forcing researchers to translate 100 years of accumulated theoretical insight into cold, quiet chambers of trapped ions and superconducting loops, into pulses of laser light and microwave radiation precise, enough to nudge a single quantum state exactly where an algorithm needs it to go. Every working qubit sitting inside a laboratory today is, in its own small way, a physical monument to that century-long effort. proof that a discovery once so strange it unsettled even the physicists who found it can, with enough patience, enough careful experimentation, and enough engineering ingenuity, eventually becomes something we can actually build, control, and put to use. What comes next remains genuinely open, shaped by research still being conducted in laboratories from California to Beijing, from Oxford to Waterloo, each pursuing its own answer to the same underlying question first posed by Feynman more than 4 decades ago. How far can we push a machine built directly from the quantum rules governing reality itself? The honest, current answer is that nobody yet knows the full extent of what such a machine will ultimately be capable of. And that uncertainty, appropriately enough for a technology built entirely around the mathematics of probability, is itself the most fitting note on which this particular story can pause, at least for now, before the next experimental result, the next processor announcement, or the next theoretical breakthrough adds its own chapter to a discovery that began with nothing more than a physicist trying to explain why heated objects do not glow with infinite energy, and grew over the course of a single century into humanity's first genuine conversation with the probabilistic language the universe has been speaking all along. Perhaps the clearest way to appreciate how far this field has traveled is to imagine explaining it to Max Planck himself, standing in his study in 1900, cautiously proposing that energy might come in discrete packets purely as a mathematical convenience to fix an equation, never suspecting that his reluctant quantum would one day be manipulated directly, one particle at a time, inside a machine capable of factoring numbers, simulating molecules, and securing communication with a guarantee rooted in the very laws of physics he had only just begun to glimpse. He could not have known that the discomfort his own idea caused him, and the deeper discomfort it later caused Einstein, Bohr, and nearly every physicist who grappled seriously with its implications, would eventually settle into one of the most thoroughly tested, most practically useful branches of science ever developed. Every trapped ion glowing faintly under laser light inside a vacuum chamber today. Every superconducting loop carrying resistance-free current at a temperature colder than the space between stars carries a small trace of that original 1900 equation, refined, confirmed, and finally, after a full century of careful work, put directly to use. That is, in the end, the real story the qubit tells. Not a story about ones and zeros being replaced by something faster or more efficient, but a story about a species slowly, carefully, rigorously learning to accept that the universe it inhabits was never quite as certain as it first appeared. And then, having accepted that uncertainty as a genuine, tested feature of reality rather than a flaw to be engineered away, finding a way to build something remarkable out of it anyway.